عليكم ورحمة الله وبركاته. My name is Abdullah Ahmed Omar Dehij, and this is Digital Logic project for Digital Logic. We have my group members Muhammad Hisham Babikir and Mus'ab Adil Ali bin Khalifa. Dedication and acknowledgement. We wish to express our sincere gratitude to our Digital Logic lecturer, Dr. Ahmed Fariz. We deeply appreciate your patience in answering inquiries and your unique ability to simplify complex concepts, making the learning process both engaging and accessible. We also commend the unwavering commitment of our team members throughout the collective effort that we have successfully navigated the challenges and shared satisfaction of completing this project. Finally, we thank everyone who contributed to our academic growth throughout this journey. We have the table of contents right here, and then we have the project overview. This project aims to enhance an existing elevator electronic controller for a hotel environment. The primary objectives are to upgrade the system's capacity from 3 floors to 7 and replace the internal logic components to specifically transitioning from D flip-flops to JK flip-flops. Furthermore, the design will integrate advanced security and functionality features, including passcode entry and visitor card indicator. Why is digital logic used in elevator controllers? The answer is digital logic is used in elevator controllers because it provides precise, reliable, and predictable control of the system. First of all, accuracy. Each floor is represented by a unique binary code, and digital logic ensures the elevator stops exactly at the desired floor without errors. 2. Predictability. The elevator behavior can be fully predicted using state diagrams and truth tables. You could design up/down counting and stopping logic exactly, avoiding unexpected movements. 3. Reliability. Digital circuits are less prone to mechanical wear and signal noise compared to analog systems. Flip-flops maintain their state until a valid input changes them, ensuring stable operation. 4. Ease of implementation. Complex operations up/down counting, start and stop at target, direction control are easily implemented using flip-flops, logic gates, and comparators. Expanding the system to more floors only requires more bits in the counter without redesigning the whole system. 5. Safety. Digital logic allows automatic stopping at the target floor using comparators and clock-enabled logic. This prevents overshooting or skip floors, which is critical for the elevator's safety. 6. Simulation and testing. Digital systems can be simulated in tools like DEEDS before building the actual circuit. Errors can be detected and corrected without risking the real elevator. Problem statement. The current elevator control system is limited by a capacity to service only 3 floors, rendering it insufficient for the proposed 7-story hotel infrastructure, excluding the ground floor. To address this scalability issue, the controller requires a significant redesign. Furthermore, the sequential logic must be migrated from D flip-flops to JK flip-flops. The project also faces technical challenge of seamlessly integrating new security modules, specifically a passcode authentication system and visitor card detection, into the expanded logic circuit. Suggested solutions. 1. Expanding the floor support. To accommodate for the requirement of 7 floors, the design was upgraded by adding an extra flip flop. This creates a 3-bit binary system capable of storing the necessary floor data, allowing the controller to effectively manage operations up to the 7th level. 2. Transition to JK flip flops. Replacing the D flip flops with JK flip flops required the development of new next state and transition tables derived from the JK excitation table. This ensures seamless state progression. Additionally, specific logic was designed to handle the saturation point, enabling the elevator to automatically loop back to the first floor after reaching the maximum height, eliminating the need for a manual reset. 3. Input management. Operational safety and security are enforced through a clock gating mechanism using an AND gate. This processes critical inputs including door status, visitor card detection, and passcode validity before enabling the system clock. As a result, the elevator will only operate when the door is fully closed and valid active high authentication signal, passcode, or visitor card is present. Here you can see our JK flip-flop tables. And here is the transition table. Also, here is the K maps that we did.
And what is the state diagram, and what's help us? It help us to kind of see like the direction of the x, which is x is just our direction for the elevator, while using the our model, which is like the 3-bit system. So it's like a transaction through state 000, which is like the 3 zeros from the beginning to 111, and the control counts upward to track the ascending floor. When x is the x0, the control count upwards to track the ascending floor, and when the x is 1, it's count downwards to track the descending floors. And this is kind of crucial, the to kind of like the logic to handles the boundaries of and the condition automatically to ensure smooth like transaction, or like smooth like sequence, or say also, or progress without require like a minimal reset, because everything here, and I'll show you in a minute after cover this, the system implementation, as you can see here, all of it start from zero, and will start from zero, so it will automatically reset here. And I'm sure like my partner Mohammed goes over it, but I would like to point out a few key points here. It's kind of like a built inside thesis simulator to foundation layers of the circuits. It's kind of like a consists of the three like a synchronizing links. One is like a GK flip flop to link together, because it's completely synchronized system. All the state, the state, yeah, sorry, these are uh, are driven directly by a single shared clock to maintain this synchronization behavior, and to clear the hardware switches. Hardware to remain at zero during the normal runtime operation. So it will run, and after that, automatically it will reset back to zero. So it will do the operation all over again. So and the specific 3 bits, it's like a configuration format, the core of to upgrade uh, of kind of like our project, safely replacing the old three like floor D flop flop. So basically, what does that mean is that when we change it to this format, this specific format of bits, we could like expand it. And obviously, the older format we cannot just stick in the tree, three floor system. But if we expand, change, sorry, the format, we could expand and make it more accurate in a way and more independent than the previous format, because we will just add like other bits and that's it. It's just binary here. We'll add more binary to it so we could add more floor. Yeah. And another one I want to cover here is the detail of security and stop logic and the green light condition. For this one, the input management and safety features for the elevator to move its must the safety green light condition, which are handling by a strict clock gating mechanism using the AND gate. And you know the AND gate must be you must have in condition is like you must have one and one, so it will go through. So that's why it's like more stricter than the OR. So the system clock will only trigger if our hardware input are high simultaneously. Mastering power is on and the start mode is active. A valid visitor keycard is deactivated and the correct authorization basic code is entered. So if all is correct, you can go through. The secret code required by our authorization system, it's like a binary combination which equal to F in hexamal format. Without this pressing PC code, the clock stays gated and the elevator remain completely locked in place. So you need to have this code so you could uh, enter. So you have the card and you have like a minimal entering code. Once in motion, our stop logic take over the circuit utilizing the matching network and build with the XNOR, sorry, and the NAND gate. The XOR gate is constantly elevating the elevator real-time position, which is the Q2, Q1, and Q0 against the passenger selected floor. The exact moment the perfect binary match is detected in the NAND gate, cutting the clock progress and stopping the elevator perfectly at the chosen destination. So that's how the system basically works. We could now go over the conclusion here, and about the conclusion, as you can see, this project was a valuable learning experience that allow us to apply all like the previous like a like a key or sorry, the key formats that we use for our this project. Sorry, for we use like the key flop flop, the D flop flop in the previous one to kind of make like a comparison. So that's really good because it's forced us to like do comparison with these flops, the and with the other gates and the other operations, and kind of work also with the key maps to kind of come with this logic for the floors. And also one of the achievement, we successfully designed the elevator control for 7 floors. During the design process, we initially overlook solution state which are affected by the system. And yeah, basically the achievement here is covering that we had some problematic uh, issues with logic, but because we expand our knowledge, not just to circle just in one formula or like a one place to learn. Now we expanded to, as again we'll repeat the key maps and the expressions, and we make like a transaction between them, and also like the other binary like a state diagram. All of these kind of help us to shape the project that we have and I'm presenting to you today. So I think that's it. And then we have reference here for our ideas and how we shape, the project. And I think that's it. And thank you for listening, and hope you enjoyed our project. Thank you.
Assalamu alaikum warahmatullah. I am Muhammad Hisham and I will explain our circuit for our elevator. So let's start our circuit. As we know, in JK flip-flops we have two external switches, present and clear, and we need to make this one and this one. So for the flip-flops to work in the synchronous mode, here we have the X input that will show us the mode for the elevator. Here we have the clock as a switch. Here we have the power, and here we have the start for the electricity for the elevator. Next, here we have the floor, and for the floor we need to enter in a binary form. So let's say we want to enter 5th floor, so we enter 1 0 1, and now we have the 5th floor. Here we have the input management. We need to enter the right passcode, which is 1011, 1011, and for the card we need to make it 1, and start the power, of course, and now it's all active high. So after we make card 1 and power and start 1, now our elevator is on the 0, and here we want from the elevator to go to the 5th floor. So all we need to do that, we need to come here for the clock as a switch and press it one time and go and check. It will go at 1st floor. If we press it one more time, it will be on 2nd floor, and we do that until we go to the 5th floor. Now it's 4th, and now it's 5. As you can see here, our elevator in the 5th floor. But if we click the clock as a switch one more time, nothing will be changed. Why? Okay, let me show you. Because here we have a similarity. Our similarity is 5. So if you want the elevator to go up, we need to change this similarity first. So let's make this floor 7. All we need to do is put all of the circuit 1 1 1, and now it's 7. So let's try. We click the clock as a switch one more time. Our elevator go to the 6th floor. If we click it one more time, now we are in the 7th floor. So now let's imagine if we want to go to the 3rd floor. We make this 0, and now it is 3. As we mentioned that 0 goes up and 1 goes down, so we do this active and click it one more time. Now our elevator is on 6th floor. If we do it 1 2 and 3, as you can see, our elevator on the 3rd floor. If we want to make it on the 0, we need to do this 0 0 0, and now click the clock as a switch 1 2 3, and now our floor is on the ground. And that's everything for our circuit. Thank you for your listening.